Welcome back, everyone, to another deep dive into all things computer science and software engineering. We've been looking at a lot of interesting stuff lately, algorithms and programming languages, all kinds of things. And today we're going to be tackling something that I
Yeah.
think is really on everyone's mind right now, and that's how to make these really cool large language models
Yeah.
more efficient. LLMs, as the cool kids are calling them.
Absolutely. It's super important when you think about actually using them, right? Not just the
Yeah.
training, but the actual using them in real world applications.
Yeah, because they're huge, right? They can be massive. And that's where today's paper comes in.
Yeah.
Matryoshka Quantization, multi-scale training for efficient LLMs, and full credit to the brilliant
Yeah.
folks over at Google DeepMind for this one. We'll also be looking at the Hugging Face page on quantization, just to give us some additional background.
Yeah, the core concept here is really elegant, and I think this has the potential to be a real game changer when it comes to deploying and using these large models.
Okay, so before we get too far into the weeds here, can you kind of give us the problem statement? What's the issue that Matryoshka Quantization is trying to solve?
Yeah, so the big problem is that these LLMs, they're huge, right? I mean, they can have billions, even trillions of parameters.
Right.
And all those parameters, they need a lot of computing power, a lot of memory. This makes them expensive to run and potentially pretty slow, especially when you need them to work in real time.
Yeah, think about like chatbots or voice assistants or something like that.
Exactly where you really need a fast response, and a major bottleneck there is what's called the decode latency. And a big part of that is just how quickly you can move all those model weights around.
Okay, so where does this idea of quantization come in?
So quantization is a way to make these models smaller and faster by basically representing the numbers in the model using fewer bits.
Okay.
So it's kind of like creating a shorthand for the information, using less space without hopefully losing too much meaning.
Can you give us like a real quick example?
Yeah, so like imagine instead of using the typical 32-bit floating point numbers, you use 8-bit integers. They're much smaller, right?
Right.
So that means you need less memory, the calculations are faster, and potentially you can even run these massive models on things like smartphones.
That sounds great. What's the catch?
Well, the trade-off is that when you reduce the precision like that, you can impact the model's accuracy.
Okay.
It's kind of like rounding numbers, right? You gain efficiency, but you lose some of the detail.
Makes sense.
So the key is finding that sweet spot, right, where you get the efficiency gains without sacrificing too much accuracy.
And it's not just like one size fits all, right? There's all these different types of quantization.
Exactly. And the Hugging Face page does a good job of kind of outlining those, talking about static versus dynamic quantization and post-training versus quantization-aware training. There's a bunch of different approaches.
Each with their own trade-offs, I'm sure.
Absolutely. Different trade-offs in terms of accuracy, speed, complexity, all that kind of stuff.
So with all of that set up, where does this Matryoshka Quantization, Mat Quant as the cool kids are calling it, I guess, fit in?
So this is where it gets really interesting. The idea behind Matryoshka quantization is that integer data types actually have this nested structure, kind of like those Russian nesting dolls.
Okay, I'm intrigued.
So you can take like an 8-bit integer and you can split it into two 4-bit integers.
Okay.
And each of those can be split into two 2-bit integers. So it's like this hierarchy of precision levels.
I see where you're going with this. So instead of training separate models for each level of precision, you're training one model that can operate at multiple levels at the same time.
Exactly, you got it. And the cool thing is that these nested models, they share their most significant bits,
Okay.
which means that you can switch between them at runtime depending on how much efficiency you need.
Wow, so you're basically getting multiple models for the price of one. That's really cool.
Right, and you can dial up or down the precision as needed.
So at a high level, how does this actually work? How are they doing this?
So basically, they're optimizing the model weights across the chosen bit widths, making sure they share those most significant bits.
Right.
It's like training multiple models at once, guided by this combined loss function that considers performance at each precision level.
Clever. So how did this multi-model approach do in testing? How did it perform?
The results were really impressive. They tested it on a couple of well-known LLMs, Gemma 2 and Mistral, and the INT and EAT4 models from Matryoshka Quantization, they did just as well as models that were trained specifically for those precisions.
Okay, that's good.
But here's the really impressive part. The INT2 models, which usually take a big hit in terms of accuracy with traditional quantization, they did significantly better, like way better.
How much better are we talking?
They saw up to 10% improvement in accuracy.
10%. Wow, that's not just like a little bit better. That's a big deal.
Yeah, it's huge, especially when efficiency is critical. So yeah, that's kind of the big selling point of MatQuant, right? You get high accuracy and amazing efficiency, kind of the best of both worlds.
It sounds almost too good to be true.
It's pretty remarkable, yeah. And it gets even better. Like Matryoshka Quantization does more than just achieve these really good results. it actually has some kind of unique capabilities.
Like what? Give me the good stuff.
Okay, so there's this thing called interpolative behavior, and what that means is you can actually extract models at bit whips that you didn't explicitly train for.
You mean like if you train for int8, int4, and int2, you could like pull out an int6 model even though you never actually trained it for that?
Exactly, and those interpolated models, they work surprisingly well.
Wow.
Often just as good as models they were specifically trained at that level. So it's like you have this slider, you can fine-tune that balance between efficiency and accuracy.
That's amazing. So much flexibility. You're not just stuck with those predefined levels.
Right, it's really cool. And then there's also something called layer-wise mix and match.
Okay, that sounds interesting.
So basically what you can do is you can combine different precisions for different layers in the model.
So like maybe you use int8 for the parts that are really computationally intensive, and then int2 for the parts that are less critical.
Exactly. It's like you're strategically allocating precision where it matters most.
That's so smart. You're really squeezing out every last bit of optimization.
Yeah, it's all about tailoring the quantization to the specific architecture and needs of the model.
Right, makes sense. Now, everything we've been talking about is focused on these integer data types, int8, int4, int2, all that. What about floating point numbers?
Ah, yeah, that's a great question.
They're still pretty common, right?
Absolutely. And that's one area where more research is needed. The authors of the paper, they acknowledge that extending Matryoshka quantization to floating point representations is tough.
What makes floating point numbers so tricky?
Well, it really comes down to the structure of floating point numbers. They're just more complex than integers.
Okay.
And so trying to apply this Matryoshka approach directly, it just doesn't work as cleanly.
So like slicing a floating point number into smaller chunks.
It just doesn't, yeah, it doesn't quite work the same way.
Interesting. So it sounds like that nested structure of integers is really key to why MatQuant works so well.
It really seems to be, yeah.
But it sounds like there's still hope. Maybe someone will figure out how to apply it to floating point numbers in the future.
Absolutely. This is a really active area of research, so I'm sure people are working on it as we speak.
I hope so. All right, so let's step back for a minute and think about the big picture. If this technology really takes off, how do you see Matryoshka quantization changing the world of LLMs?
Well, I think it has the potential to be truly transformative. Like,
Yeah.
first and foremost, it could significantly reduce the cost of deploying these LLMs.
Right, because right now it's pretty expensive to run these things.
It is. It's very resource intensive, but if we can make them more efficient, then suddenly they become accessible to a much wider range of users and applications.
So instead of needing these massive data centers to run these models, you might be able to run them on, I don't know, your smartphone or something.
Exactly. Imagine running powerful LLMs on your phone or on small embedded devices.
That would be incredible.
Right, and that opens up so many possibilities, like personalized AI assistant, all kinds of stuff.
Yeah, it's like you're democratizing access to these cutting-edge technology.
Exactly. It's really exciting. And then on top of that, we could also see much faster and more responsive LLMs.
Right, that's important for things like real-time translation or chatbots.
Absolutely. No more waiting forever for a response.
And with this ability to change the precision on the fly, depending on the task, you can really fine-tune things.
You can adapt to the complexity of the task.
Right, so if the LLM's doing something really hard, it can use a higher precision.
Right.
But if it's something easy, it can just dial down the precision and save resources.
It's like the LLM has adaptive intelligence or something.
Exactly. That's a great way to put it. And this dynamic adaptation could revolutionize how we interact with these models.
It really could.
From our smartphones to our cars, they could be everywhere.
Yeah, it's an exciting future.
It really is. Before we move on, can you quickly remind our listeners where they can learn more about all of this?
Yeah, so the best place to start is the original research paper, Matryoshka Quantization, Multi-Scale Training for Efficient LLMs.
Easy enough to find online.
Yeah, it's readily available. The authors are Pranav Nair, Paranjay Datta, Jeff Dean, Pratik Jain, and Aditya Kusapati from Google DeepMind.
And of course, we also recommend the Hugging Face page on quantization if you want kind of a broader overview of the topic.
Yeah, absolutely. Understanding the basics of quantization will really help you appreciate how clever Matryoshka quantization is.
All right, well, I think we've covered a lot of ground today. We've talked about the principles of Matryoshka quantization, the potential benefits, the challenges that still lie ahead. But as always, we've only scratched the surface, so we've really dug into the technical details here. But what does this all actually mean for our listeners out there? What's the takeaway?
Yeah, that's a great question. And I think it really depends on who you are and what you're doing. Like if you're getting ready for, I don't know, some big technical meeting and you want to sound really smart and you're talking about LLMs, well, being able to drop some knowledge about Matryoshka quantization,
Right.
that's going to turn some heads.
Definitely going to impress some people.
Yeah, for sure. But if you're actually working in this field, developing and deploying these LLMs, I think this is like a glimpse into the future. We're
Yeah,
talking about solving some really big problems in terms of cost and efficiency.
right.
And that's going to open up a whole world of possibilities for new products and
So it's
applications.
not just some abstract research paper.
No, not at all. This has real-world
They're going to
implications.
change things.
It really could. And even if you're just, insanely curious about this stuff, I think Matryoshka quantization is just a really cool example of how, a clever idea can lead to something really powerful and elegant.
Yeah, it's like they took this idea of Russian nesting dolls
Right.
and applied it to these massive AI models.
It's pretty brilliant.
It is, it is. So as always, we like to leave our listeners with something to think about, something to chew on. What's a question that people should be asking about Matryoshka quantization?
Okay, so here's the question. If this works so well for, quantizing existing models,
Right.
could we use this multi-scale approach during the initial training process?
Oh, that's interesting. So not just quantizing after the fact.
Exactly. What if we built this into the training from the ground up?
Right, like bake it in.
Yeah, could we create even more efficient models, even smaller models, right from the start?
Now that would be a game changer.
It would be huge. It might mean we need to rethink how we do training,
Right.
but the payoff could be massive.
Yeah, big challenge, but big potential reward.
Exactly.
Well, I have no doubt that brilliant minds are already working on this as we speak.
Oh, I'm sure they are.
And we'll be here to report on what they find. Well, on that note, I want to thank everyone for joining us on this deep dive into the fascinating world of Matryoshka quantization.
It's been a pleasure, as always.
Until next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible in the world of computer science and software engineering.